I want to get into more technicalities. The first talk was trying to explain to you the nature of the hierarchy problem in such a way that if anyone ever tells you, there's no hierarchy problem because I used dim reg, actually, and I can absorb everything into my definition of M. Higgs, and these people talking about the hierarchy problem are idiots, you can say, well, actually, no, you need to think about calculability and blah, 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 and or just slap them and walk off, whatever you prefer. Don't. Please don't hurt anybody. Slap them with science. So we were discussing the hierarchy problem. That was the goal. Now we're going to go into some technicalities. We are going. I promise you, we will get very quickly today towards the actual new problems new ideas for the weak scale that I want to discuss, and then tomorrow will be the much more radical new ideas that I think are possibly the most exciting. But sort of motivated by the structures that I would like you to be aware of, so that we can even discuss sensibly the new ideas that are being discussed, and also sort of motivated by something Nima said in his talk. His colloquium talk, which was, the Higgs could be like a PIon. I'd like to discuss possibly one of the oldest, not the oldest idea for the weak scale, but one of the oldest ideas for the weak scale, which is the Higgs like a PIon. As he said in his talk, currently, and even probably when we get to the end of the LHC era, what we really know about the substructure of the Higgs is that it could be just as much a composite state as it turns out that the PIon is, within a factor of a few. The compositeness scale of the PIon is a factor of, depending on which units you like to use or what you like to compare or how you like to define it, a factor of say 4 or 5 times smaller than the sort of the Compton wavelength of the PIon. And it turns out that by the same sort of measure, the scale at which we've constrained the compositeness of the Higgs is also only about a factor of, probably 4, 5, maybe 6 times smaller than the Higgs. So as far as the Higgs is concerned, we look at it with the LHC, and what we see is a ball, and then we can sort of probe a little bit closer inside, and we can only probe a factor of, say, 5 times smaller than the Higgs, and still it's sort of looking like a point particle. But that doesn't mean it is a point particle. It just means that we don't know that that's the scale we've gone to. Unless we build a bigger microscope, we can't see smaller things. And I think this is a very useful way of thinking about the Higgs, because it's also a very useful way of thinking about the hierarchy problem. And it's also a very sensible question. If I didn't know much about particle physics other than reading the PDG and staring at the structure of the standard model, I think probably one of the most sensible things that I could ask is, well, we've now got this scalar. When did we last see scalars that have gauge interactions? That was the pions. So maybe it's just like a pion. And it turns out that this is not an insane question. So how does this look in practice? What if the Higgs were a pion? What sort of structure are we talking about? We need to put some mathematical flesh on these words. And I asked you all in the first lecture who knew about the Goldstone's theorem and who understood the Goldstone's theorem, and many of you purported to both know and understand Goldstone's theorem, so I'm going to use it a lot in the first half an hour here. So the idea, if we think about the pions, is that is the best way to understand the structure of pion physics is to understand the structure of global symmetry breaking. And when we study Goldstone's theorem, we learn that if we have a spontaneously broken global symmetry, that will give rise to a massless scalar particle, or not necessarily pseudo, it would give rise to a massless boson for every generator of the symmetry that has been spontaneously broken. We also learn that when we study these structures further, that the symmetry is not really broken in the sense it's always there, but it becomes hidden, it becomes non-linearly realized. So we go from a linearly realized phase to a non-linearly realized phase. So the number of Goldstone bosons we get, n, is equal to the dimension of the original group, continuous group G, minus the dimension of the remaining group H, where we've spontaneously broken G to H. And always by spontaneously broken, I mean gone from the linearly realized symmetry. This is the linearly realized symmetry. This is still a linearly realized symmetry, and everything else has become non-linearly realized. And for the pions, what happens is that we're going from SU2 left to SU2 right. Sorry, SU2 left, SU2 right. Sorry. To SU2 vector. So this is the spontaneous symmetry breaking pattern. Where does this happen is that we can see that we have a pair. If we just think for a moment about the up and down quarks, we have a pair of left-handed quarks. We have the up and down left-handed quarks. We have the up and down right-handed quarks. And they condense. They pair up with each other and condense. And what this means is that we end up breaking to the diagonal subgroup of these two groups. So independently, now forget about the quark mass terms at the moment. If we don't have mass terms, independently we could do an SU2 rotation just on left-handed quarks and an SU2 rotation just on right-handed quarks, and nothing would ever change in the Lagrangian. But purely due to QCD making them confine and condense, you spontaneously break that symmetry, and all you have left over is an SU2 vector, which tells us that then the number of pions we expect, n pi, will be equal to, so there's 3 generators here and 3 generators here. There's 2 groups, so we have 2 times 3 minus, we've got a leftover SU2, which is this, minus 3. So we expect 3 Goldstone bosons. Okay. Now they would have been massless, and I can hear you screaming in your head, but they're not, the pions aren't massless. And that's good that you're screaming that. But this can still be used as an organizational principle if you have some sort of separation of scales or if you have some sort of small parameters. And we do have a small parameter, which is the quark masses. Now, if you study the quark masses, you'll see them in the PDG. I think the down quark is something like, I can't remember, 6 plus or minus 2 MeV, and the up quark is something like 4 plus or minus 2 MeV. But an MeV is well below the QCD scale. So what this means is that we have an approximate SU2 left cross SU2 right symmetry that has been spontaneously broken. We expect Goldstone bosons, but there's a little bit of explicit breaking of that symmetry, which is the quark mass terms themselves. So we expect Goldstone's theorem to be approximately true. So if it's approximately true, we expect to have something that's approximately massless, but not identically massless. We expect to have something that's much lighter than the QCD scale, and that's exactly what we get. So there's some small parameter, and you can understand that m pi squared is much less than f pi squared, for example, because we have some explicit breaking, which is, m quark is much less than lambda QCD, essentially. Now, going back to this idealized world of the first lecture, imagine we had never gone above the QCD scale, so we'd never known that there were actually quarks for sure. We would have hypothesized, nonetheless. This is about, our ability to guess what comes at the next microscopic scale isn't just dependent on the hierarchy problem. We have many tools, and one of the tools you would have had here, and this is a tool that was used, is that, well, we have these 3 light scalars. So a good guess would be that in the UV there's some theory, we don't even know what it is. In the UV there's some theory with some continuous symmetry which had, say, some number of generators that's broken to some other continuous symmetry. Yes? Oh, no, not, sorry. This is like, sorry, these don't even have the same dimensions. Thank you for it's like, think about it as like m rho squared. Like 4 pi-ish, or G star, the strong coupling. What I wrote there, they're not even commensurate. You can't even compare them. Thank you. That's like saying m top is close to v electroweak. It's stupid. Thank you. Okay, so we would have guessed that there's some spontaneously broken symmetries, and there were 3 generators spontaneously broken, and that explains why there's 3 light pions. Are there any questions about that structure? Because this is a very useful story in model building in many places. And it comes up, I should say, I'm sure you don't all want to work on the hierarchy problem. You'll work on dark matter and all sorts of things. If you wanted to work on models of composite dark matter, this is exactly the sort of thing you would employ. It's also a story that doesn't have to be strongly coupled. So we see it a lot when we're working with strongly coupled theories, because it's one of the few handles we have. When we work with strongly coupled theories, we don't have perturbation theory. So we have to rely on the few tools that we have, and this is one of them. But it's also something that you can use, and we will use actually in the last half of this lecture, for purely perturbative theories as well. So even if you're working with something that has totally perturbative couplings, it's very useful to structurally organize how you view models in this way. So if there's any questions, please ask, or any questions about the last lecture at this stage. Nope. Awesome. Okay. So now let's think about the Higgs. So when we study the Higgs multiplet, we see that it's a complex doublet, so you can call them whatever you want. I'm going to call them H1, H2, H3, and H4. So there's really 4 degrees of freedom in here, 1, 2, 3, 4. And what that tells us is that we will need, if we wanted the Higgs to be like a PIon, we would need to have the dimension of G, whatever continuous group we have, minus the dimension of H is greater than or equal to 4. If we're going to hope to build a theory where the Higgs is like a PIon. Now, there are many, many ways you can do this, but also we will need to be careful because there's always going to be more to the story. In fact, in here we have gauged a subgroup of these symmetries, which is electromagnetism, which ends up meaning that the charged pion is charged, it couples to the photon. And as we saw yesterday, that explicitly breaks the symmetries that we were using in the first place, which is why we get a mass correction to the charged pion that shifts it relative to the neutral pion. So here I overlooked something, which is gauging of subgroups. So in reality, if we're being general, we need to think about the fact that we could also have subgroups of this group that are gauged and subgroups of this group that are gauged. So I'm going to call those, give those groups a lowercase letter. So what we really need is that dim of G minus dim of H minus dim of little g. This is the gauged subgroup of big G. Plus dim of big H. This is the gauged subgroup of big H. Is greater than or equal to 4. So why do I say that? The reason is that if we are spontaneously break a gauge symmetry, as we know, the Goldstone bosons will be there. They will be physical, but they will be eaten. We won't see them as massless degrees of freedom. We'll see them as the longitudinal component of a massive vector. So they'll be gone. Now, we're pretty certain that, to a very high degree of confidence, that the Higgs is not a longitudinal component of a massive vector. If it is, we would have seen at exactly the same mass the transverse components. So that means that we'd better not have the Higgs being a longitudinal component of some gauge subgroup. So for every guy that we lose, every Goldstone that's been eaten, we still need to have, not for everyone, but overall, once we take account of the ones that have been eaten, we still need to have 4 left over. Because there's 4 degrees of freedom in the Higgs doublet. We're not breaking SU2. So we want the standard model to emerge, just like here with the pion, electromagnetism is not broken. Yes? So this is minus. So this is minus the eaten ones. Sorry. So we're not using this story yet to break SU2. Yeah, exactly. So we need 4 scalars to come out. This, yes. We will deal with electric symmetry breaking at a later stage. So what we want. So what am I really saying here? We want. So think again in comparison with the pions. So we imagine that at something that is analogous to the QCD scale, there's some junk. And what emerges from that junk is the standard model at the weak scale. Just like here, there's some junk at lambda QCD, and what emerges below is all the meson physics. So we want our meson physics to literally be the standard model or a close approximation to it. Okay, excellent. So now that we're going to try and embed the Higgs in this way into some global symmetries, we can play with lots and lots of global symmetries. This is, if you think about it, this is a model builder's dream, because all you need to do is pick a G and H where you have this, and then you write a paper, and then you pick a different G, and this is what happened, right? For probably in a very intensive way for about 3 or 4 or 5 years. There was a lot of this, different models with different global symmetry patterns. We're going to just do the simplest one. It turns out that the simplest model doesn't has a bunch of problems, so it's not a good description of nature, but it will at least illustrate the main features for us. So what we will pick is big G is SU3, little g is SU2, big H is SU2, and little h is SU2. In other words, what I'm saying is G is SU3, and we're going to gauge an SU2 subgroup of SU3. Okay, now you can see if you do the numerology, we've got a problem here because we get that n is actually equal to 5, not 4. So we get one extra scalar. Now, this is good news because you've got at least 4, so you can hope to embed the Higgs. But it's bad news because you've got some extra scalar. It turns out that extra scalar, well, we don't need to talk about him. We can talk about him later if you wish. That extra scalar is a standard model singlet, and you can actually make it heavy. It's interesting to study, but its properties are relatively model dependent, so we won't talk about it. So what this means is we have some SU3 global symmetry, and we want to spontaneously break it. Yes.
Do you not want like to contain CSM, right? Because SU3, like in standard model, you need like SU2 plus SU2.
Ah, yes, absolutely. Yes, secretly, I'm always saying cross U1x and cross U1x everywhere. Yep, absolutely. That's a very good point. Pardon? Oh, also color, yes. But I'm talking about the stuff where we're doing the symmetry breaking. That will all just sit in the background the whole time. These are excellent questions. Any more? Yep.
I probably missed this. What is the other one?
So this is the gauged subgroup. And this is the unbroken subgroup after we spontaneously break. And this is the bit of that subgroup which we've gauged. So here we just never break it. There's SU3 and we gauge SU2 and we just never break the SU2 bit. So, okay. Any more questions? Great. So a second second question. So who has heard of CCWZ? Okay, much fewer. Who has ever seen, if you spontaneously break, say you have some abelian Higgs model, so we've got just a single complex scalar. So we'll have some Lagrangian like d phi squared minus something like phi squared minus, let's call it f squared squared. So this is just an abelian Higgs model. Phi will get a VEV, and you'll spontaneously break the U1 symmetry, you'll get a single Goldstone boson. Have you seen this where you write phi as something like rho plus f, say over 2. I like to keep my 2's. Rho plus f over root 2 e to the I, let's call it omega over f. Phi written in this way, where omega is the Goldstone boson, and rho is what we would call like the Higgs. That's the heavy scalar that gets left over. Who hasn't seen it written like this? Not many people. Okay, great. So if you haven't seen it, this is basically, so you can always choose to parameterize your degrees of freedom as you wish. There are smart ways of doing it, and there are dumb ways of doing it. It turns out that if you are working with a single complex scalar field here, you could have written something like phi is equal to phi real plus I phi imaginary. That's one possibility. Or, it's totally up to you. You could choose to write it like this. Phi is rho plus f over root 2 e to the I omega over f. It's entirely your choice. Now, if you write it like this, you will see that the pseudoscalar bit will, in the end of the day, become masses when you expand it out. Yes? Right, yes. I've not gauged anything. There's no gauge symmetry. This is just a global U1. No, this is not big D. This is little. This is partial. But yes, as you say, so this is in polar coordinates. As we know, when we're working with any coordinate system, we can choose Cartesian, polar, spherical, polar. It's your choice, right? If you work with it this way, you'll see that phi I is imaginary. The imaginary part, sorry, is massless, but it will have interactions, and you will do a lot of work to see, you know, when you start quantizing this theory, you'll do a lot of work to see that you've actually still got a massless particle. If you work in this basis, you see that it's massless straight away because plug phi into here, and you see that phi squared is just rho plus f squared over 2. There's no mention of omega. So omega doesn't even have a potential. There is no omega in the potential at all. So you automatically see that it's massless. So this is the smart way of doing it. This is the dumb way of doing it. Well, it's not that dumb. There are dumber ways of doing it. But yes, you get interactions from the kinetic term, but you see that you always have derivatives on omega. So it will stay massless. You have a shift symmetry. OK, so now it turns out that when we spontaneously break non-abelian symmetries, the same thing holds. There is a generalization of this, which is known as CCWZ, which is the way of parameterizing all of the low energy interactions. So here, rho, you'll see that he gets mass squared of order lambda f squared, but omega is massless. So say you're working at energies well below the mass of the radial mode rho, then all you've got is your massless Goldstone boson. So you can actually, to a good approximation, essentially forget about rho, if you wish, and just work with phi is f over root 2 e to the I omega over f. And then all you see is you get a kinetic term, essentially. And you will get, from the effects of rho, when you've integrated him out, you will get other higher dimension operators involving omega. But you can work, if you just want to parameterize the low energy physics without committing to any UV completion. Here the UV completion is the radial mode rho. But you could have spontaneously broken this symmetry in many ways. So maybe you just want to know what the properties of a Goldstone boson from U1 symmetry breaking are like without ever committing to a specific thing. Then you actually just work with this field here, which is what we call the nonlinear realization. We call it nonlinear because when you plug this in, you see that you will have a shift symmetry. That instead of this symmetry being something where a phase multiplies a field, like here you'd have the symmetry would be a phase multiplying this field. Now the symmetry transformation is that omega goes to omega plus some constant. And you will see that when you plug this into the action is invariant. So this is the U1 version of CCWZ. But we can parameterize these Goldstones here from our composite Higgs model in exactly the same way. So we work, so big phi there was a field that was a representation of the U1 symmetry. So what you want to work with is something that's still in a representation of the SU3 symmetry. So we work with something that we call sigma, which is a triplet, which is a representation of the SU3 symmetry. So what that means is we write down all of the interactions and couplings and all of the sort of operators that you might wish for in an SU3 invariant way, but we parameterize the Goldstone bosons non-linearly, just like we did for the U1 model. So sigma is now e to the, we can write it like this, e to the pi a, I'll say Ta over f, where Ta are the 3 broken generators. All multiplying the vacuum, so which in this case would be 0, 0, f. And we tend to call this something like sigma 0. By the broken generators in the SU3 matrices, we're assuming that these are the generators that we're breaking, and this is the SU2 subgroup, which remains unbroken and that we actually are gauging. Are there any questions about that bit? Because we're going to start using this now for calculations. No, excellent. Okay, so we can put this in. So these generators are just these guys here. The singlet guy was the one who lived here, but I said we can forget about him to a good approximation, so let's forget about him. So now we've got, the generators are just these matrices here. You've got something like, 1, -1 here, or I and things like this. And you plug it in. you can literally plug it in and take the matrix exponential, and you see that sigma is just the following. In terms of the different fields, you can write it in terms of the Higgs fields as I H1 sine of H over F all over H over F, I H2 sine of H over F all over H over F, and then F cosine of H over F, where here H is equal to H squared is H1 squared plus H2 squared plus H3 squared plus H4 squared, which is, in normal language, we would write that as a mod of big H squared. Okay, so this is, you can do this as an exercise if you wish. Just plug it in, and this is what you get. So now we can learn all about the low energy properties of this theory without even knowing actually how this symmetry was broken. It could have been some gauge group, it could have been some other gauge group, fermions in different representations, all these sorts of things. We don't care. We're effective field theorists. We're just working at low energies. Yep. Yes. And gauged. Absolutely. So that's, so you can see that, you know, to a good, say to a good approximation, if we take F, if we this is looking like a Higgs doublet, where we've got the Higgs doublet in the first two components, and we've got essentially nothing in here. If we take H over F to be very, very small. Great question. Any others?
What did you get from? Second line?
This second line. So you literally plug this in. So the pi a's. So the pi a's are this. So pi a would be, you know, pi 1 would be H1. Sorry, I should give a lower index, perhaps. Pi 2 is H2. Pi 3 is H3. Pi 4 is H4. Now I'm scared about the i's. I might write down the wrong thing, but the generators would be like T1 would be something like big 0 here, and then something like 1 minus 1, 0, 0, 0, just the usual SU3 matrices. So you literally put that in there, and you get a big matrix. Multiply it onto this, which is the vacuum that spontaneously broke the symmetry, and this is what you get. Yes, the four that are broken. So there's 5 that are broken. These, so all the generators that live along these components. This guy was the singlet, which we're going to forget about for the meantime, because we can actually give him mass in a. He's not so important for the story, but also is there as a low energy remnant. Is that clear? Okay. Great. Yes. Yeah, that's what I was worried about. The I can't remember if it's 1, 1, and then we'd have you know, I minus I for the other ones and things like this. Yes, but I always worry. I can never remember which what once I've got the I in here, which ones they are. If it's I times the Pauli matrices or not. But you seem to know, so I trust you. Okay, excellent. Any other questions? This is good. Yes. Yes. Yes, to a certain extent, although we have to be honest, and it's not arbitrary because we've gauged an SU2. Had we not gauged an SU2 subgroup, then any F is good. You could distribute F as you wish amongst the 3 components. Pardon? Right, exactly. So, but now we're saying that. So in some sense, now again, we could have had it anywhere, and then we just gauged the other bits of SU2 appropriately. But we're sort of doing something funny because we're saying we're breaking. We break SU3, and everything else we gauge. Yep.
I think still that it's just going to redefine the you can always rotate it.
No, but yes, but you have to remember that you gauge the rest, the SU2 that's left over.
But H over F is sort of parameterizing the angle between the unbroken and the gauge.
Well, we haven't even broken SU2, so there's no angle at the moment because SU2 is still totally unbroken at this stage.
No, I mean the unbroken SU2 inside the SU3.
Yes.
There's that choice, and there's the choice of which SU2 you gauge, and H over F is sort of rotating
Well, no, if we'd chosen any other thing and still gauge whatever SU2 is left, H over F would be the same, unless we change the magnitude of the breaking.
Yeah, but it's just another defined.
Sure, but the redefined H over F is still the same. Doesn't change it. In other words, you could pick, so long as you could distribute F any way you want along here, and you only gauge the SU2 that's left over, and you're still good to go. And it will look like this thing here will have the same H over F, but it will be distributed. It will be an SU3 rotation of this, will be the leftover thing. But it's not going to change the value of H over F.
So there's one thing is that you don't, I mean, we just say, you say I'm gauging SU2, right? But once you're saying which SU2 is unbroken, that's sort of arbitrary, right? That you can always rotate.
Which is what I'm saying.
Right.
Yes.
And so, but that rotation is exactly the Goldstone rotation, right? Which is what takes
No, the goldstones are in the broken generators.
Sure.
That rotation doesn't touch the goldstones, other than to do a global. So it'd be some unitary 3 by 3.
Well, but that's because you've chosen the break-in to be exactly, I mean, you've chosen the unbroken one to be the gauge one.
Yes.
So you can just choose, I'm not doing that.
Oh yeah, if you do something different, then you get a different answer. But if you gauge the SU2 that's unbroken, this is what you get, up to an overall global rotation. But if you gauge some other thing that is also now partially broken or something like that, then I still don't think I understand the question. Anyway, okay. So, any other questions about this? Yes. 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 So that's why I've unapologetically always discarded. So there is this generator, 001, along the diagonal. And that is the Goldstone but he is neutral. So you can see that this bit here will be the SU2 bit that's gauged. And he will just live in here. So he's there, but for our purposes, we can forget about him because he is not playing a role in electroweak symmetry breaking. But he is there the whole time. So actually the full thing has this plus a bit involving that scalar. Any other questions? Here. So there's F cosine H over F. Okay. Super. Okay, so now we can go ahead and actually see what happens. So, what happens with the gauge interactions? Probably wipe this off. So this is just like electromagnetism is to the PIon. So we need to think about the gauge interactions, and to introduce gauge interactions, we do the dumbest thing you could imagine, which is we promote a standard partial derivative acting on sigma just becomes the covariant derivative acting on sigma, where now the covariant derivative is what you would expect, but now we have the gauge terms. Lambda of A, where lambda A are the matrices now. You see I'm not calling them T. These are the matrices in the SU2 direction. So these are these generators in here, which are the normal electroweak, guys. So we see that then we have explicitly broken the global symmetry because we've gauged some subgroup. And the way you can see that is, imagine now, so we've got d mu acting on sigma. Now imagine we do an SU3 rotation of d mu sigma, you know, the kinetic terms. For example, we have d mu sigma all squared. Now say we do an SU3 rotation on global SU3 rotation on sigma, so we multiply it by u, which is just some unitary 3 by 3 matrix. Then this is no longer unchanged. It would have been unchanged if we just had the covariant derivative, because we've got sigma dagger sigma. But now between the sigma dagger sigma, we also have these gauge bosons living in this SU2 corner here, and the SU2 rotation is going to jumble all of this up. So it's no longer the same. It isn't invariant. You do an SU3 rotation, you end up with a different Lagrangian, so it's no longer a symmetry. So the gauging has actually broken the global symmetry, just in the same way that the electromagnetism, the coupling to the photon, broke the shift symmetry of the charged pion. So it's 100% analogous. There's sometimes a criticism of these models where people say, this is totally crazy. You know, you're picking in global symmetry, and then you gauge some subgroup of it. So you're actually breaking the symmetry explicitly, and now the Higgs has this coupling to the gauge bosons. It's all totally ad hoc. It's as hoc as nature already did to us. So I don't, it's not so mad. But what this means then is just like the pions. So we have two predictions. Just like the pions, we will get corrections to the mass squared of the Higgs that we should expect, because now we've broken the global symmetry. So there's absolutely nothing protecting us anymore from corrections in the UV to the mass of the boson, just like the corrections we got to the charged pions. So we should expect, now as I said, we're working in the low energy theory. I haven't actually specified how we broke this global symmetry spontaneously. I'm just saying it happened, which is what happens, you would have to do if you'd never discovered QCD and you just had the pions. So we should expect that there should be corrections to the Higgs mass that go like g squared, where g in this case is there's also g primes, but let's just work with the g at the minute. G squared over 4 pi squared times whatever the mass scale of whatever is living at the cutoff, just like we had for the pions. So what this means is that there's going to have to be something turning up around the corner, and if you want these corrections to be not much larger than the Higgs mass, this would probably happen around a TeV or something. Now what happened for the pions, what turned up was the rho meson, a vector, and that's exactly what we expect to happen here if you have some strongly coupled theory. So you would get a vector that also shows up in your theory, and it's a resonance, just like the rho meson was a resonance. And what this means is that at colliders that can probe the sort of the TeV energy scale, you should start to see resonances showing up if the Higgs is a composite. So this is a really neat experimental prediction, right? We're talking about the low energy theory in the same way as the pions. We're actually predicting the existence of some resonances showing up around the TeV scale, because just like we did with the pions, because there's no protection now for the Higgs mass. So if the Higgs mass is around 125 GeV, that gives you a constraint on how big these corrections can be, so something could show up. And how would these rho mesons of this new strongly coupled theory actually show up at colliders, how we would see them? There's a number of signatures, but probably the simplest is that literally colliding QQ bar, for example, at the LHC, or E plus E minus at some very high energy E plus E minus collider, could produce these heavy, we usually call them rho prime mesons, which could decay into something like muons that would stick out like a sore thumb. So if you studied, for example, the differential event rate at your collider, d sigma by dm mu plus mu minus, as a function of m mu plus mu minus, then there'd be the usual QCD background, not QCDs, the usual standard model background from the production of Z's off shell, QQ bar through an off shell Z into mu plus mu minus. And then sticking out like a sore thumb, essentially like the rho meson did, there would be, you would start to see some sort of resonances like that. And it turns out that this puts a strong constraint on fully fledged models of composite Higgs. There's some other aspects of this that we can already, without doing any work, so this was all just in full analogy with the pions again. There's some other aspects of this that we can extract very rapidly, some experimental predictions, just by the fact that this funny formalism here, this CCWZ expression, isn't just H1, H2. Okay, so if it were just like in the standard model where you have just literally the standard model Higgs, you have something like, in this language it would be 0 H1 and H2, and none of this funny trigonometric business here. But this funny trigonometric business is carrying with it the fingerprint of compositeness. It's carrying with it a little prediction which is saying, look, guys, there is actually some non-linearly realized symmetry hidden in here, which corresponds to the the spontaneously broken parts of the linearly realized symmetry in the UV. And it's going to do something. And what it does is it will modify things like couplings. So without doing any work, we can stare at this. So we have the usual couplings to the Higgs bosons come through this covariant derivative here. So we have the W and an SU2 matrix living in this component here, acting on this. So our coupling to the gauge fields will look something like W mu, and then we'll have a G, and then some matrix. For the W's, it's just the off-diagonal matrix. But this is all schematic. Multiplying, let's say, I don't want to get told off about my plus ones and minus ones again. 0, 1, 1, 0, and then things. Oh, let's put actually just the whole thing in. 0, 0, 0. Then acting on this guy here, so we get things like H1 sine blah blah blah, H2 sine blah blah blah. So that tells us that when we go to the fully electroweak broken vacuum, we will get couplings to the Higgs, which look like, let's call it CW, is scaling like 1 relative to the standard model, plus correction factors that are going like sine of H over, sorry, cosine in the end of the day. Things like this. No, it's sine. Sine of H over V over, of V over F, because we've set the Higgs to the electroweak broken vacuum. We're expanding about that vacuum, and something like V over F. So you're going to get corrections. Now this is very model dependent, so I'll just write down plus something like it's usually, or minus something like a sixth, or it depends on the theory, V squared over F squared. So already we've learnt that in this class of models, not only do we expect to see some resonances showing up that look sort of like a heavy version of the rho meson, but also the Higgs couplings are not going to be fully standard model-like. There will be corrections that scale like V squared over F squared. So if F is really far away, then this correction will be small, but if F is nearby, then this correction will be big. And this is exactly what underlies Nema's statement, actually. So essentially the corrections to things like Higgs couplings are constrained to now be pretty small, like say 20% or 10% from LHC data. And that tells us that F is probably bigger than about 600 GeV. And those two pictures he had on the board, that's really where it comes from. Any questions about any of that? Yep.
So should we expect that the higher Higgs resonance will be also spin 1, or do you have a principle dictating that if you get a resonance, it has to be spin 1, like for the rho?
That's a great question. Yeah, I wouldn't call it the Higgs resonance because it's like another meson of a QQ bar bound state in the UV. I wish I could tell you that yes, there's a theorem, but there isn't, I guess. But it always is what shows up. So if you put in, I'll give you two answers. If you put in a strongly coupled gauge theory and calculate it on the lattice, for example, just like you see in QCD, you typically get your Goldstone bosons, and you get heavy sigma-like fields, which are just heavy scalars, and spin 1 guys and spin 2 guys and so on. That's sort of, where in some sense, where the old part of where the motivation for the old 1970s style string theory was coming from, because you were seeing higher and higher spin resonances. You tended to get a tower, that's my Northern Irish accent, tower, T-O-W-E-R, of spin resonances. So you do expect to see spin 1 guys, but I can't tell you definitely. Also, there are holographic jewels of 4D composite models like this, 4D strongly coupled theories. They're holographic jewels. And in there, you see these higher spin resonances showing up, and you see very clearly where they come from. For example, if you have a gauge theory that lives in the bulk, they would look like the Kaluza-Klein states of the gauge bosons and things like this. So my answer is that generically they show up. I've never seen an example where they wouldn't show up, but I can't promise you that they would. Yes?
And then how do we estimate what mass we would expect to see them at?
Ah, very good. Excellent question. So the mass, so we have to, so dimensionally, F here is not a mass scale. There's no particle that will ever have mass F. It's like the Planck scale. There's no particle that has mass the Planck scale. It's impossible. So we have to have something that has dimensions of mass, and it has to know about F somehow. As we push F up, we expect the mass to go up. And that's actually, and this is what we see sort of in QCD as well. M rho, we usually parameterize it by G star F. Now G star is the sort of the size of the coupling in the underlying theory. So for a super strongly coupled theory, G star would be something like 4 pi F. We don't expect them to ever be heavier than 4 pi F. But if the theory starts to become more perturbative, they could be lighter than that. Super questions. Yep. It's like the PIon. It's composed in this class of models. It's composed of quarks. So we're living below that scale. But so the idea is that just like the PIons, there's above a few TeV. There's quarks not of QCD, but yeah, we never see them. We're working below the strong coupling scale. But if you went above the strong coupling scale, you would see the new strongly coupled gauge group, and you would see the new quarks.
Why can't that make them out?
No, indeed. So yeah, okay. So very good. So yes, I mean this whole formalism can work for things that are more perturbative, or where you might not necessarily think of it as having quarks in a strongly coupled gauge group, like in extra dimensional models. Indeed, you're right. So there's a notion in which, because also, I can't specify from the low energy theory the exact strongly coupled gauge theory because of universality. That could be all sorts of things. But I think composite. So yes, indeed. Let's. This is a very good point. More generically, we call these class of models PNGB models, pseudo Nambu-Goldstone boson models, which is a more honest way of. I was trying to relate it to Nima's talk about compositeness, but indeed, yes, it can be more generic. You may not need to have necessarily extra heavy quarks. Yep.
So you showed us how to break the symmetry, like using the gauge interaction by gauging a subgroup. But I assume there are other ways of breaking it slightly so that
Right.
half of the Goldstone boson is still remains small.
Right, exactly. So, yeah, and we don't do this, we don't gauge the interactions because we don't want to break the symmetry. We want to keep it as good as possible.
No, it breaks make the Goldstone boson pseudo.
Right, exactly. Yeah, we don't want to do it, but we're obliged to because the Higgs interacts with the gauge bosons. So we're not doing it for an aesthetic, it's not a choice, but it's the opposite. We don't want to have to do this, but we have to do this. We would rather find a way of not breaking the symmetry, then we could have an even larger scale separation. And when I get to the top Yukawa, you'll see there's many other ways that you break the symmetry, or you could just break it explicitly. There are many things you could do. Yep.
Sorry, can you but where does the
So the rho isn't a Goldstone, so it's not a part of this story. It just tends to show up, just like with QCD. Yep. Well, no, but it depends what you mean by the hierarchy problem. So indeed, one of the nice things about this class of models, if it is one where there's fermions in a strongly coupled gauge group, is that yes, you would have no hierarchy problem because you don't even have a scalar to talk about, which is why there's no hierarchy problem for the PIons. They're perfectly natural. But we have to be a little bit careful related to this point over here because there could be some other UV completion where we don't think of it as being like PIons. Maybe it's something crazy that's more like extra dimensional or something like that. There are other UV completions. But yes, but because motivated by that, we don't want to this all to be too heavy, otherwise we're in trouble. Okay, so let's get on to the top quark interactions. So this is finally where we start to diverge from the usual story, from analogies with the pions, because the pions themselves don't have interactions. Well, they do have interactions with, for example, protons and neutrons. They do have interactions with fermions, but the quarks to us are looking pretty elementary-ish, certainly the light quarks. So we have to somehow introduce interactions between this field here, which contains our goldstones, and the fermions. Now, we could try and do exactly what we did for the gauge sector. So what do we do for the gauge sector? As I said, we just gauged a subgroup. So what we did is just sort of almost by hand said, well, it is by hand because we're model building, but we said, well, maybe in nature, just some part of this global symmetry is gauged, and we're sort of setting by hand the gauge bosons along here to 0. We're just saying they don't exist. Okay. As I said, that sounds crazy, but nature did it already, so let's not worry about it too much. What about for the top quarks? Because those are the biggest interactions that we need to worry about. Well, we could just by hand say, well, I'm going to introduce now a triplet, because everything is SU3, so we have to write everything down in terms of SU3 representations. I'm going to write down some triplet, which contains the usual doublet, TB, and I'm going to do what I did in the gauge sector and just switch off the field I don't like. Okay? So we just set it to 0. And then we can write down that the quark Yukawas just look like this. We've got lambda q dot sigma, and then some right-handed field, let's call it t right. This is lambda top. But then we will get exactly the same story. So what we've done by switching off a field, we get exactly the same thing that we get by switching off a field here, which is that by writing an incomplete representation, we've actually explicitly broken the symmetry. So the analogous story will occur, and we expect then that we will get corrections to the Higgs mass that are going like, there's 3 of these guys because of color, so we get something like 3 lambda top squared. I think it's, well, it's all regulator dependent anyway, but you expect to get corrections that scale in this way, just like we did for the Higgs. Now this is telling you now you don't want this guy, the eventual Higgs, to be heavier than 125 GeV, so this puts an upper limit on this, and it tells you that actually you really want lambda to be less than around, something like 500 GeV before you have to start tuning the theory in some way. So that's telling you you've got some stuff around the corner, just like this told you there was some stuff around the corner, and then you expect these rho prime mesons. This is telling you there must be some stuff around the corner. And pretty soon, right? Because we're talking about LHC energies and we're talking about 500 GeV. So we should have seen this stuff. We would naively expect to have seen this stuff. We can actually make the story a little bit better because we can add fields that we call top partners. And what we do is we just complete the multiplet. We do something different from what we did with the gauge sector. And we say that Q is now just T, B, and let's call them big T. So we complete it. So now we've got a full-on representation of SU3. So life will be good. We have the usual interaction, T right. And we now don't expect any mass corrections because we've written everything down in a fully SU3 invariant way. So there's no explicit SU3 breaking here, which is great. Can anyone tell me what the problem with this theory is? Right, exactly. So this Yukawa, for example, with the top right-handed top is only going to give mass to one of these guys. So from this Yukawa, we'll get a massive top-like particle, and this guy here essentially remains massless. So it's a linear combination in the end of the day, but you end up with a massless fermion and it also turns out with weirdo hypercharge. So you're in big trouble. Bigger trouble than this story. So then what we tend to do is that we add in an extra partner for this guy that he can pair up with and a mass. This is again sort of by hand. So we've added in an extra top partner that can pair up. Sorry, a top partner that can pair up with this guy to have a Dirac mass term. And now we have this theory here is fully respecting SU3, and this part of the theory, and this part of the theory is breaking it. So now we expect the mass corrections to be at most proportional to 3 lambda top squared, up to some logs, 8 pi squared, then m squared, because m is the only parameter breaking the SU3 symmetry. If we send m to 0, we should recover SU3 symmetry, so we should recover small mass corrections. But this is where we hit, finally, new-ish ideas for the weak scale. Because this guy here, you see that this mass correction here is telling you that if you want this theory, if you don't want to have to start tuning between, say, these corrections and those corrections and bits and pieces like that, or some other UV corrections that may be there just coming from the UV theory itself, then it's telling you that you want this m to be less than around 500 GeV. But if this m were less than around 500 GeV, then unless we've really missed something very obvious in the analysis of the LHC data, which is possible, right? There are many ways if you produce these particles via QCD, you can maybe hide them from some bizarre decay chains or something like this that are hard to see. But it's probably unlikely now that we have missed 500 GeV colored fermion at this stage. So we have a puzzle, right? We don't want the Higgs to be like a PIon, but if we think that that may be what nature has chosen for us, then it looks like we sort of rather model independently now have to expect colored particles around, say, 500 GeV and new resonances around a TeV or so, and neither have shown up. Oh, and modifications of the Higgs coupling, which I've rubbed off. So this pushes us towards a paradigm that has been repopularized. It's sort of, I think, waning. The interest is waning at the minute. But it's known as neutral naturalness. And there's a class of models that were written down in actually 2006. The people behind this were Go, Chaco, Birdman, and Harnick, writing down a variety of different models. And I think I wasn't, I was an undergraduate at the time, so I didn't follow what people's opinions were. But I feel by looking at the literature that they wrote down these models to try and circumvent these types of problems. And they went largely unnoticed because there wasn't this problem at that time. The LHC hadn't been built, so we hadn't seen a lack of top partners because we hadn't gotten to high enough energies yet. So these models sort of sat quasi-dormant and largely were overlooked for about 10 years. And then around 2015-ish, interest in these theories was reignited because we started having to come face to face with this empirical fact that we hadn't seen colored top partners. So people started to really study these theories, and they're not, this class of theories are known as neutral naturalness theories. They're not textbook material, but they are something that has been worked on in the last 4 or 5 years. And I think people are still partially interested in, although a lot of the low-hanging fruit has maybe been covered at this stage. And the idea is to really push on, I keep talking about expectations, based on QCD, this is what we saw. Based on this theory, we expect, because of this, to have some sort of colored guy around the corner and so on. These are naive expectations. And what those guys did was say, well, how hard can we push on these naive expectations? And how far can we take, for example, for the case of a goldstone like Higgs, how far can we take that paradigm whilst somehow hiding the extra particles? So what I want to tell you about is known as the twin Higgs. So who's heard of the twin Higgs?
One question.
Oh, sorry. Yes?
So drawing the parallel to the actual PIon, shouldn't the parity properties of the, if one can measure the parity of the Higgs, should that be related in some way with the soul?
Very good. So you're saying, well, the Higgs is a scalar and not a pseudo-scalar.
Right.
So, yes, no, yes, that's a very good question. It depends really. Here you don't necessarily see that the Higgs is a pseudo-scalar at this point. Working through this, which is telling you that you don't have to in these classes of models. You don't have to have, for example, always CP odd like decays. But on the other hand, the sort of things that are messing with that are the way that you've written the Yukawa couplings and things like this. So to the extent that you've messed with the fact that it's a goldstone, you're messing with those sorts of expectations, like that it would be CP odd. So for example, anytime you're producing the Higgs through a Yukawa interaction or through a gauge interaction, you're already messing with the fact that it's a goldstone in the first place. Yep. Yes. So you don't need to worry about metastability, because you go up through a few TeV and there's no such thing as a Higgs. Yes, yes, yes. And furthermore, I've rubbed it out sadly, but the modifications of the Higgs self-coupling scale in this class of models, naively, as always you can mess with these things, scale in the same way as the Higgs gauge coupling modifications and also the Yukawa coupling. So they're all going like v squared over f squared. Now, it's an awful lot easier to measure a Higgs gauge coupling than it is the self-coupling. So, by the time, if the Higgs was a PNGB like this, by the time you measured a modified Higgs coupling, you would have seen absolutely everything else before that. Any other questions? Yep.
Why do you expect the partners to be
Because unless we start tuning, so you can see from this example that the correction scale, like m squared, lambda top is order 1. So we want this number to be not, it's 2. If you want this number to not be larger than 2 times 125 GV squared, which is big M of big H squared, then this guy shouldn't be more than about 500 GV or 400 GV. I think that's for like a 10% tuning or something. Okay.
M should be the same order of magnitude as lambda?
So here we don't know. So here lambda is where all the strongly coupled physics kicks in, which we need to be quite high. So this is an enormous problem. So if you didn't have these top partners, this is a good question because I should have said this and I didn't say it. But if you didn't have these top partners, this naive expectation, which is just going by what happens with electromagnetism in QCD and things like this, is telling you that if there's no tuning in the theory, the whole strongly coupled sector would have to live at like 500 GeV. And then, definitely we've not seen particle events, exploding with incredible, like happened when we were discovering, scientists before us were discovering QCD. That's what we would have seen. But why we introduce this is that we can now take lambda, if we have this, then the theory as far as the fermions are concerned looks above 500 MeV, for example, can still look very SU3 invariant, and we can take the cutoff away. So we keep these top partners here, and they're that's why we call them top partners, really. They're taming the divergences. So then we can take all of the strongly coupled physics heavy, and so long as we keep these guys light, then all you would expect to discover is the top partners, not necessarily all the strongly coupled stuff. Okay, super. All right. So let's consider now the twin Higgs. Yes, so I should have put this in. So you can find, they're not on the I don't think they're on the archive. I haven't put them on the archive, but there are some lecture notes of mine on BSM theory. I'll put a link up to. You can find them at various courses, and there's lots of links to all the references. There's lots of references to all of this stuff in those, so you can just Google them, but I will also get it put up on the webpage. All right, so how does the twin Higgs work? So the twin Higgs is a beautiful and cruel idea. The idea is, so let's play the same game, but now we'll start with an SU4 symmetry. So we'll have some guy, I'm going to call him Big H. This is not the SU2 doublet, this is now an SU4 fourplet, which will get a vacuum expectation value that looks like this, so everything's pretty analogous so far. And we will have a scalar potential which looks something like the usual Higgs-like potential, but remember this is a fourplet. Then we expect to get, we've spontaneously broken SU4 to SU3. So the number of Goldstones now will be 4 squared minus 1 minus 3 squared minus 1, which is 7, which is way, way too many. Okay, but here comes the cruelty. So the idea is that now we gauge the two SU2 subgroups. So now we've got SU4, so you imagine the transformations or a great big 4x4 unitary matrix. Now we're going to gauge the two diagonal SU2 blocks, which is sort of what we already did in any case with the SU3 model. It was a diagonal block. So now we're going to gauge the two diagonal SU2 blocks. So now we write big H is HA, HB. So this is an SU2 field. This is an different SU2 field. There's SU2A and SU2B, or SU2 and SU2 twin. They're called different things. And we gauge the two SU2 blocks with equal gauge couplings.
So this is inside the unbroken SU3?
Yes, exactly. So we're gauging. So now we have an SU2 and an SU2, and nothing in there. Okay, so we give these guys, and we will give them identical gauge couplings. Now let's do the same estimate that we did always, every single time, right? We've gauged the subgroup, that means we've broken the symmetry. So we expect to have now, we're not using the Goldstone's theorem anymore because we've got explicit breaking of the symmetry. Yes? You have a larger global symmetry, which is an exchange symmetry, but you have only what you've gauged. The gauge group is what you've gauged, so you've got 3 generators here, 3 generators here. Yep. Yeah, I mean, there are much more immediate things that are going to hit us in the face. But we will get to that, and that will be that will be actually the Achilles heel of the twin Higgs will be related to precisely your question. But we're going to get there. Okay, so now let's do exactly what we did with the PIons, exactly what we did with the SU3 model, and we expect now that there's going to be a correction to the Lagrangian because we've explicitly broken the symmetry, which is going to go like g squared over 16 pi squared. I was at 4 pi squared, HA squared, because we've gauged this subgroup, so that's going to mess with that. And now there's another one, g squared over 4 pi squared, HB squared. Okay, we've gauged that guy, he's going to mess with this. So all of this, and times something at the, actually no, let me write this differently to point out an underlying assumption. Times lambda squared. So this is what we did both times in the past. Now we have g squared over 4 pi squared Higgs b squared lambda b squared. Okay. Now something curious happens whenever lambda a is equal to lambda b. So imagine the physics at the cutoff, whatever's up there, and you can specify it. You can write down perturbative models for the symmetry breaking. You have some non-perturbative symmetry breaking. It's your choice. But imagine that it's identical between the A and B sectors, so that the cutoffs are actually identical. Now, can anyone spot something remarkable about this mass correction in terms of the symmetry story? No professors? Exactly, it's SU4 symmetric. So, it's SU4 symmetric. So, what do we have here? We've got that this is g squared over 4 pi squared HA squared plus HB squared. But that is just lambda squared h squared, which is just like the mass term in here from the cross term in the first place. So something really remarkable has happened, right? We started with an SU4, then we explicitly broke it by gauging two subgroups. But the fact that we gauge them in the same way means we've got an SU4 invariant, which means that this correction can never give you a mass to the Goldstone boson, because it's SU4 invariant. So that's the magic of the twin Higgs. I've not ever said anything about twin standard models, and we're going to get there, but I think it's a common misconception that the twin Higgs is about adding loads of particles and choosing couplings and things like this. That structurally, this is what's happening. You've symmetry that keeps two sources of explicit breaking the same, and if you can then keep the physics at the cutoff the same, you accidentally get something which is SU4 invariant, even though it had no right to be a priori. So this term here, we do get these mass corrections to the big Higgs, but when big Higgs gets a VEV, and we have all of the Goldstone bosons, they will never ever sense this, just like when I did the U1 abelian Higgs model. Do you remember when I did the nonlinear realization, e to the I omega over f? And I plugged that into the U1 invariant potential. Omega completely disappears from the potential, and similarly here, the Goldstones will completely disappear from the potential. They will know nothing about this correction. So you get no corrections to the Higgs. And no quadratic divergences from the gauge sector. Yes? Right, but then you would have no electroweak symmetry breaking. So you could have that. You could have do this. But then we wouldn't get the standard model out of it. Any other questions? Nope. Super. Okay, so now let's do the top Yukawa. So let's do exactly the same trick. We're going to now explicitly, so remember when for the SU3 story, we explicitly broke the symmetry in the top sector by writing down an SU3 multiplet and just by hand deleting the third component. So now we're going to write down two SU4 multiplets and just by hand delete the third and fourth components in one hand and the first and second components in the other hand. So now the Lagrangian looks like this. So we've got lambda top HA, so this is a doublet, QA, which is a doublet, let's call it UCA, plus lambda top QB, UBC. And we're set, just like we set these two gauge couplings to be equal, and we can enforce that with a symmetry, which is an exchange symmetry, where you take everything and you swap it. So this is not, a tuning of any sort. We can set these two to be equal by an exchange symmetry. So then we get exactly the same story. So now the corrections to the mass of this guy are going like 6 lambda top squared over 4 pi squared lambda squared, if the physics at the cutoff is the same, multiplying h squared. So I just move it across. So this is an SU4 invariant, so this gives you no corrections to the Higgs mass. There's no quadratic corrections to the Higgs mass. Oh, sorry, yes. Long day. Okay. So structurally, we can see that we now have a way of adding in, of having an SU4 symmetry and adding in particles in such a way that's enforced by a symmetry, which is an exchange symmetry, where all of a sudden this issue about quadratic sensitivity to the physics at the cutoff has vanished. So this is a very, very powerful tool. However, there are sources of symmetry breaking that we cannot, SU4 symmetry breaking that we cannot avoid. What's essentially happened here is that we have a theory where because of the exchange symmetry, we get an accidental SU4 symmetry at the quadratic level. However, that SU4 symmetry does not need to remain even at the quartic level, or if you went to dimension 6 or and so on. And that's why it's an accidental symmetry. Now you might say, well, that's a bit of a weird thing to do, but also this is accidental symmetries have also shown up in nature before. For example, baryon number. If you specify the gauge group of the standard model and of the matter particles, you simply cannot write down a baryon number violating relevant operator. The only operators you can write down are irrelevant. which means that at low energies you have an emergent or accidental symmetry that needn't actually be present at high energies at all. And that's what we're seeing here. We have, because of the exchange symmetry, we're seeing in the IR theory more than the exchange symmetry emerging. What we're seeing is accidentally at the quadratic level, you get a full SU4 symmetry. But there are problems. This is why the question about RG evolution was so pertinent. Because what we need, if you think about it, when you study this, potential here, this is a 4-plet. So this is like HA, HB in a column all squared. So we can write it out that this looks like, maybe I should do this over, let me do this over here, actually. So this is looking like V equals lambda over 2 HA squared plus HB squared minus F squared all squared. But we also have these sorts of interactions with the gauge groups and these interactions with the tops. And actually, these will be the most important. You mentioned gauge ones, which are important as well, but the most painful ones are actually the tops. But I hadn't even mentioned the tops before you asked the question, so I'm sure you would have said top Yukawas had I done that. But now, independently, this top Yukawa is going to make everything involving HA run, because it will run proportional to lambda top squared. And this top Yukawa is going to make things proportional to involving HB run, like the parameters of the B sector potential. But these fermions here don't know anything about these fermions here. So these guys deal with the A sector, these guys deal with the B sector, but there's nothing in that RG running, at least at one loop, is going to generate mixed terms between the A and B sector. That might sound like that's going to be a good thing, but it's actually a terrible thing, because it means that you get corrections at one loop. I'm just going to write one of them down, which go like 6 lambda top squared. This is from RG evolution, 4 pi squared. For example, log of the UV scale over F. I've behaved badly again. These are not really commensurate. There's some sort of gauge coupling, and there's some coupling in here. Let's call it G star. The important thing is that these corrections scale like HA squared, HA to the 4, plus HB to the 4. So this is the one loop correction to the scalar cortex coming from those Yukawas. So it's like we see in the standard model. But if you see, this does not respect SU4 symmetry, but does respect the exchange symmetry. So at some level, when we spontaneously break at the scale F, this term here is going to have to give you a mass term for your Higgs, because it's explicitly broken the SU4 symmetry that you were using. So what have we learned? We've learned that accidentally, at the quadratic level, we accidentally have an SU4 symmetry, so we expect no quadratic sensitivity of the Higgs mass to the cutoff. But we've not achieved a huge amount, because we do, at the quartic level, get log sensitivity to the cutoff here. Now, if we want this correction to be small, lambda had better not be too big. So we cannot use this trick to arbitrarily decouple the physics at the cutoff. And in fact, it means that you can only live about a factor of 1 loop or so below the cutoff. So nonetheless, in this theory, something is going to show up at around, say, 2 or 3 TeV for this reason. Because essentially, once you put in the spontaneous symmetry breaking here, this guy will give you a correction to the Higgs mass squared, which is going like F squared times 1 loop. This 1 loop correction here. Okay. Any questions about that? Yeah, this is the 1 loop RG contribution to the cortex. There will be other ones at higher loops, but and there's also a gauge one at 1 loop as well.
Just want to be oriented on the motivation.
Yes.
To show that there is a class of possible things to seek something very specific that might be worth.
So the motivation for all of this is to try and guess what the origins of the Higgs sector are. Right? We want to know.
But there's a generic mechanism, something very specific. You can get into the discussion.
Okay. So this is a sort of a generic mechanism, but it's not as generic. So right. Okay, I understand. So. Right. Exactly. So this seems like we're moving further and further from generic statements about symmetry breaking and goldstones towards a very particular construction that doesn't seem to be, it's getting further and further away from the things we know. And indeed, that's the case. These twin Higgs models are not as generic as typical PNGB type scenarios. But it turns out that they can be generalized. You can actually generalize this structure to much larger global symmetry groups and so on. Present data. Yes, so that's the next point. So what is really interesting about these models is actually what happens at the LHC. Because, so we had all of this sector here. We learned that we have a Higgs doublet charged under the standard model SU2. And we have another doublet charged under a different SU2. So as far as we're concerned, Higgs B, living in the fourth, I should just write the thing down. Higgs B, oh I did, here it was. Living in the second two components is charged under some different gauge group. So this is charged under SU2 left cross SU2, cross U1 hypercharge, sorry. But this guy here is charged under, we call it a twin version, so we're about to get to that. SU2 left twin cross U1 Y twin. This is completely standard model neutral. You can't produce him at colliders apart from the interaction here between him and the Higgs. Furthermore, these guys here are standard model neutral. They're not charged under the standard model gauge group. They're charged under SU2 twin. And I'm about to tell you why I call it twin, why it's called twin by the authors. And furthermore, in terms of color, these guys are of course charged under SU3 QCD. But in order to get the same corrections at both sides, all you need is that these guys are charged under some SU3 QCD that has the same gauge coupling, but it needn't be ours. So in fact, what we've done here is introduce a whole load of standard model neutral stuff. Not a single one of these particles that we've introduced has any standard model gauge charges or any standard Yukawa couplings to standard model particles. So what we've actually done, and I've intentionally introduced this backwards because I did not want you to think about this as starting off with copies of the standard model. I wanted you to think about it in terms of symmetry structure. But what we've actually done is we've taken a standard model, and we've introduced an entire copy. Yep. Well, better than gravitationally. And we've introduced an exchange symmetry. If you think about it, so now so by standard model twin, what I mean is now we've done this story for every Yukawa coupling. We've done it not just for the tops, but also the bottoms, the charm, the strange, the up and the down. So the standard model and standard model twin. We've ensured that there's an exchange symmetry. And what that does is it keeps the couplings the same on both sides, the values, but it's not the same gauge groups, it's different gauge groups, but the same couplings. It means we've kept the Yukawa couplings the same on both sides, and it means that in the UV, you had better have it that the cutoff, the physics at the cutoff is the same in both sectors. Otherwise, you're totally doomed, right? If we had lambda A was different to lambda B, this would never have worked. And this is an important point. And the last thing we've done is that we've said that there's some Higgs portal interaction. Which is this guy here, that V is looks like lambda over 2 H squared. Now this is H standard model squared plus H twin squared minus F squared. So this is just a generic SU4 invariant potential. And we could have small pieces that break the SU4 symmetry, but they have to be small. So this is all we've done. We've taken the standard model, completely copied it, and assumed that at the scale of the UV cutoff, that we have an approximate SU4 symmetry in the scalar potential. And there's a negative mass squared. Yep. Okay. Can I have 2 more minutes because it's the last talk? Okay, super. So what we've done is we've introduced stuff that's totally neutral. So the problem we had before, if you recall, was that we would have these row particles which coupled to standard model, but also the top partners for a typical PNGB model were colored, so we would have expected to produce them in abundance at the LHC. Now we've introduced a whole load of stuff that is impossible to produce, and the only way you can produce it is that when we square this, we get cross terms between Higgs and the Higgs and the twin Higgs. So any way you can possibly hope to probe this theory at a collider has to involve the Higgs. And it turns out that the best, your best chance for that is by taking, because here this has very standard model-like physics, so that your best chance for that is to do something like produce a standard model like Higgs. And through this interaction, there'll be a small mixing between the standard model Higgs, not necessarily that small, a mixing between the standard model Higgs and the twin Higgs. So we can mix through a coupling that's proportional to this lambda to a twin Higgs. And the twin Higgs can decay, for example, through, there are many possible things it could do, through a loop of twin tops into twin gluons, which then twin hadronize. Some of which, maybe you've got a twin B meson, which couples to the twin Higgs so that it can decay through very off-shell Higgses in ways that can mix back into the standard model Higgs and go to, for example, standard model objects. So what you have, so the Higgs is 125 GeV. So what this means is that the final, if you can produce them, the standard model end products at the end of this decay chain will be less than something like, if you're getting pairs of them, 60 GeV center of mass energy. But in terms of the typical transverse energies, the PTs, they'll be very, very soft, 10 GeV or something like this. So this model is very, very hard to search for at colliders. Yet, it is a scenario in which the electroweak scale can be relatively natural. That's one signature. The other signature is, do you remember with this SU3 model, because this was a PNGB in the CCWZ formalism, we end up with corrections to the Higgs couplings that were going like V squared over F squared. And it's the same story here. We're really starting with something that's SU4-ish and spontaneously breaking. So we can't forbid having corrections to Higgs couplings, which are scaling like V squared over F squared. And this is actually sort of the strongest constraints on these models. The Higgs coupling measurements tell you that F has to be larger than, say, 600 or 700 GeV. So you have to play a little, there's a little bit of tuning you have to do to realize that. But nonetheless, this is one example of a class of models. And it goes even beyond that. You can do similar tricks for supersymmetric theories as well. So this is not restricted to composite or PNGB type models, but it can be generalized, although I feel like it has a more natural home in this sort of framework. And even you may ask, in what ways can you embed this into different stories, and how can you end up with an approximately SU4 symmetric potential? But it turns out there are ways to do that. So for example, if you embed this structure into supersymmetry, then it's quite natural because of SUSY non-renormalization to end up with a theory that's very like this, with small SU4 breaking terms arising accidentally in the supersymmetric theory. So there are a myriad of different model building directions to go in. And also what's perhaps even more compelling is that they point at classes of signatures that if I had just written this down, imagine I'd said none of this story, none of the fairy tale, and I just said, look, guys, at the LHC, we need to search for a Higgs that might mix with a Higgs from an entire twinned standard model, and then I want you to go and search for twin hadronization that might decay, and an experimentalist would just say, not a chance, guys. But it tells you that there are very exotic signatures at colliders that may, before you understand some setting in which they may arise, they may sound completely crazy, but nonetheless they're very worthwhile to search for. So I think that's one of the successes of the twin Higgs paradigm has been to highlight that when we talk about naturalness in collider physics, we don't need just to be talking about stops quarks at 800 GeV. It's a broad arena of signatures that could give us our final handle on the origins of the weak scale. And I should really wrap up there, I guess. Yes.
If you have extra light gauge bosons in the same structure, is that light technology?
Well, they're not light, right? The mass of the standard model gauge bosons are like GeV, which is 8-ish GeV. And so the mass of these guys will be GF. Ah, no, very good. Okay, so the twin photon is lethal. It's ruled out cosmologically, so you have to, well, not totally lethal, but you have to either play games with cosmology so you never reheat in that sector too much, so you don't get too much twin photon, or you can start to mess with the model and break twin electromagnetism but not break standard model electromagnetism so that the twin photon is heavy. But my personal perspective is if you start to go down that road, you had better maintain that the cutoff physics stays the same, respects the exchange symmetry. So that has to be only in the IR, otherwise you can't really trust the whole story.
I'm just going to ask one more thing. This process looks like it will predominantly give missing energy signatures.
Right.
So when you say that, I don't know the couplings of the mass scale. So
Yes.
what are the chances of seeing such a process? That first of all, how do you know if you see two standard model particles and missing ET?
Yes.
That's also, I guess, is optimistic.
Yes.
So how do you know that it comes from such a model or not?
Well, you don't. You don't. So you would need to see lots of things. So say you started to see that at the LHC, then you go and speak to politicians and say, look, guys, we really need to build a collider that can go to higher energies, because you would want to unravel this whole story, but that would take a lot of work and it would be a long time. So you don't, this signature is not unique to that, because the signature, things like B's and missing energy, could come from a whole host of different models. Yep.
And if you can create one twin standard model like this, you could possibly also create infinitely many, right? Just by going to larger and larger groups.
Right. So you can create many. You can't go to infinitely many because you'd renormalize the Planck scale, and gravity would be strongly coupled. But no, you can go to lots. And in fact, there's a generalization of these models in the context of orbifolding, known as orbifold Higgs and things like this, where you can actually realize this structure where you've got a Z3 symmetry, where you're rotating, permuting between 3 or 7 or whatever. So this is a generalizable story. Now, it's not as generic as the standard PNGB setup. You have to realize these accidental symmetries in some way. You could ask, where is this Z2 coming from? But that's that's our own aesthetics. We can't decide for ourselves what nature is going to be. But yes, it's generalizable. Any other questions? If there are no more questions, I just want to reiterate: don't slap anyone. That was a very bad joke, and I'm worried about it.